Hello, and welcome to our fifth lecture in the Jabrah reinforcement learning series. And this lecture is just going to continue from where we left off. And today our focus will be on policy improvement. So if you remember from our last lecture, we talked about the policy iteration algorithm. That was going to be our first reinforcement learning algorithm in this series. And we had split it into policy evaluation and policy improvement. So now we are actually going to be focusing on the improvement part of the policy. So in order to do that, we need to go back to our ongoing example, the one we had here, whereby we had this kid again who stole money from his parents and is trying to navigate through this maze to reach the KFC. And if he gets caught in this, he gets a negative reward of say -5, and if he gets in any of those states that we've got sticks, so here he gets all of these areas have a -5 reward, but if he ends up here, he gets a reward of +10. So the idea is to maximize the cumulative rewards you get as you go through this maze. And if you remember from the last video, we spoke about what we would consider a state in this environment, what our actions are. So I'll just briefly reiterate. So let's say this is our initial state as 0, and so our states actually were corresponding to the cells that we're in, and the actions we could take were pretty much say left, right, up. Oh, that should be move up or move down, if it's possible to do these actions in whatever state we're in. So this was the basic example that we had going on, and in this lecture we're actually gonna start on a new concept that will help us improve our policy, because if you remember from the last lecture, we assumed that someone just gave you a policy and we were evaluating how good that policy is, right? And how do we evaluate how good that policy is? If you remember, we're computing something known as the value function, right? This is what we were computing, which we called like V of S, how good it is to be in a particular state under the given policy pi. So if you forgot about this, just go to the previous lecture and you'll remember what we're talking about. So now that we know what the value function is, one of the reasons we actually compute this function is so that it can actually help us find better policies. So let's say someone gives you a policy, and the policy is like always move right. That's the policy, right? So someone gives you a policy and say pi of s for all s is an element of capital S, right? This is the policy that they give you, like this is supposed to be equal to right. That's the policy that they give you, right? This is their policy. So this is a bad policy, because like you start from the state, you move right, you move right, you move right, you move right, and at the end you just end up here, and then you get stuck in the state. So that's a bad policy. So once someone gives you a policy, the goal actually is to figure out ways to improve that policy. That's what the policy improvement is about. First, we try to evaluate how good the policy is by computing its value function. Then we try to improve the policy. So that's what the focus is on this lecture. Now, in order to improve the policy, I'll have to introduce a certain notation that is used widely in reinforcement learning, and that is the use of Q values, which is iterated in this format. So you've got Q pi S comma A. So what is this? What does this actually mean, right? What is Q pi S comma A? Well, we spoke about what the value function is, but the Q function actually help us know the value of a state and action pair, right? So the value function tells us how good it is to be in this state. But the Q function actually, if we split this like that, so this is action 1, which is move up, action 2, move right, action 3, move left, and action 4, action 3 move down, and action 4 move left, right? So we have these 4 actions we can take. So we want to evaluate how good is it to be in this state and take action 1. How good is it to be in this state and take action 2 or 3 and 4 and so on, right? That's what this Q value is. So it's essentially trying to compute, like, under policy pi, how good is it for me to be in this state and take this action, right? Right, and maybe compare it with how good it is for me to be in this same state and take action 2, and so on and so forth. That's what the Q function is. It's basically, we're just breaking down the value function into all its possible actions, like all the possible actions we can take in that state. So given that, now that we know what the Q value is actually indicating, if you remember from the previous lecture, we had actually denoted how we represent the value function, and if you remember, it was something along the lines of what is v pi of s. We had said that this is the expectation of a pi of rt plus 1 plus gamma gt plus 1 given s, right? Given you're in the state s, you get the reward, and then what is the value of all the cumulative rewards you get after that. And of course, we also say that this is the same as expectation of a pi of rt plus 1 plus gamma v, right? That's v under pi of st plus 1, right? Given s, because this essentially are supposed to be the same eventually, because the value of being in this state, right, is like the reward you get after that, and following the value function of the next state under policy pi, and so forth. That this was basically how we had defined the value function. So how do we define now q pi of s comma a? So there is not that much difference here. Actually, the only difference is that we have an extra condition, right? Like in our expectations, because it's expectation of a pi of rt plus 1 plus gamma v pi st plus 1, as we had before, right? Before it was just given s, but now it's given s comma a. Why? Because this is after being in the state and taking action a. Then we compute this expectation. That's how good it is to be in this state. So that's what the Q function actually represents. Okay. So we can actually break this down even further, right? And we can say q pi s comma a, right, is equal to the summation over s prime comma r, and we're going to take the transition probability s prime comma r given s comma a, s comma a, multiplied that by r plus gamma, right, times v pi of s prime. Right. So how is it different from before? Like in the case of the value function, if you remember, we had an extra term behind this, right, which was essentially we're multiplying this as well by, if you remember, in the case of a value function, we're multiplying by this expression, right, I given s, right, for a. This expression, because the reason we're doing this was because the policy has the possibility of actually being a probability distribution whereby we might actually take a given action with a certain probability or another action with a different probability. But here we don't have this term because we already know which action we're going to take. It's represented in QS, A. So there is no probability distribution over the action space anymore. We're just looking at the value of that action, right? So this, we don't need it anymore in this scenario, right? So this actually helps us establish like okay, what is Q pi S comma A, what is what you call this, and why are we actually interested in this term, right, to begin with. So this takes us to our next concept called the policy improvement theorem, right? The policy improvement theorem. So as I had mentioned earlier, what is happening here is that if you're given a policy, right? That's how we're doing policy evaluation. Someone just gives you a policy. It can be a random policy, it can be a stupid policy, but they give it to you, then you evaluate it. So now you start questioning yourself. Okay, this guy gave me his policy, pi of s, this function. How do I improve this function, right? How do you improve this function? That's the question, right? So let's say we changed this policy, right? Just a little bit. In one particular state, we just take a different action, and after that we follow the same policy, right? So what I mean by that is you are given a policy which is like move right, for instance. Let's go back to our example here, maybe it will be clearer. Sorry. So you're given a policy move right, but maybe we make an extra policy that, okay, when you're in this state, move down instead, right? Then after that, follow the same policy, move right. This is kind of like what we're doing. So in order to better understand what I mean by this, I'm gonna show you like, so we are following the same policy pi, right? Q pi of s comma a, right? This is what we're currently doing. If someone gives us a policy, and so all the values, we can represent them in this form. But then we say, actually, let's change things a bit. Let's have q pi s comma pi prime, which is a different policy, s, right? Okay. So the policy improvement theorem states that if this is greater than or equal to v pi of s, right? If this expression is greater than v pi of s, then, so if, let me just remove this to remove any confusion. So if q pi of s comma pi prime s, if it's greater than or equal to v pi of s, then pi prime, right, the new policy, must be as good or better than prime, right? So if we just make a change, right, that in just one state, right, we make some change that, oh, okay, let's follow pi prime in this state, then after that continue with our following v pi, then that means that pi prime must be at least as good as pi, right? That's how we improve the policy, right? That's what it means to improve the policy in this sense. So of course you might ask yourself that we only changed the policy in one state, right? Just one state. and let's say it's better in the state, but does it actually follow that this theorem would hold in all of the other states that we didn't change this policy, right? So there's a proof as to why this theorem actually works, and I'm gonna go through this proof, like as to why when we change a policy at a particular state, right? Why is it that it should follow that if we follow the previous policy, then this new policy must be as good or better than the previous policy, right? So, okay, that might be a bit of a food for thought, but let me just try to make it a bit clearer. Okay, so we are comparing policy pi and policy pi prime, right? This is what we're trying to do. So if we apply pi prime on a particular state, right, and then end up following policy pi, right, if this gives us a better value, that means that pi prime is better than pi. That's basically what we're saying overall. So let's go through this theorem. That's the proof of this theorem. So what is the claim? The claim is that v pi, right, of s, this is less than or equal to q pi of s comma pi prime s. So this is the claim that we're making, right? And we say that this holds in one state, right? This value is better than this one. So this is given. We computed it and we discovered that this is the case. Why are we saying that this means, was actually our claim, our proof is that this means that v pi prime of s, right, is greater than v pi of s, right? So, or even further, pi prime of s is better than pi of s. This is kind of like what we're trying to prove here. So, given this, there are two formulas that we're going to need in order to make this much simpler for us, because we're just going to be reapplying the same formulas here. And one of them, we've already gone through them. They are shown in the slide. Was it this one? Yes, this is the slide. When we say q pi s comma a is equals to this expression here. So let me just rewrite it in the next page. Sorry. So like what we had here was that q pi, let me do it in a different color so that it's a bit clearer. So we have that q pi of s comma a, right, is equals to the expectation of rt plus 1, right, plus gamma, right, v pi, right, st plus 1 given s comma a. So this is essentially what we have, and we're given s comma a. I'm just writing it roughly. I'm going to write it again over here for more clarity, but just try to keep this in mind, right? So the other one that actually we need is from the previous slide again, when we said q pi of s comma pi prime of s, right, is greater than or equal to v pi of s. This is the other proof. So of course I'm saying this now, but if you're not actually interested in this proof, you can skip this over, but for those that are interested, I'll just keep going on. So those that are not interested in the proof, just take it as is, that this, where was it again, that this policy improvement theorem actually works as is, that q pi s comma pi is greater than or equal to v pi of s. You can just take it as is. But here now going to the proof. So let's actually split this even further. We say that this is the expectation, right, of RT plus 1 plus gamma V pi ST plus 1, right, given ST, comma, sorry, given S, comma A, right? But what is S and what is A in this case? I should clarify that. A here is actually equal to pi prime of S, right? So why is this the case? Because we are actually taking the action pi prime of S. This is the action. The action under the new policy is what we're taking, right? Not the old policy. So we can of course just rewrite this as the expectation over pi prime, right? The expectation now is over pi prime of RT plus 1 plus gamma V pi ST plus 1 given S. That's all. Why? Because now since we're taking the expectation of a pi prime, we're just assuming that, okay, this is the policy that we're actually going to follow, pi prime in this case, right? So here now we reapply the same formula here. Oh, sorry. The formula here, that's what we're reapplying. So this is equal to, actually, it should be greater than or equal to expectation of pi prime by RT plus 1 plus, right? And at this point we have gamma, but since we say that this V pi of S, right, is going to be less than or equal to Q pi of S comma pi prime S, that means we can actually replace this expression here with this one here and still maintain the same inequality, right? So that's Q pi of S comma pi prime S, right? This is what we have here, but in this case, actually, I should rewrite it in this same format of using ST plus 1. Sorry about that. So ST plus 1, right, comma, pi prime, right, substituting pi prime of ST plus 1 again, right, and this is all given S, right? This is the stage that we're at, and we can simplify this further and say this is actually equal to expectation again over pi prime of RT plus 1 plus gamma times, again we say that Q pi ST plus 1, or rather more generally Q pi S comma A should be equal to this expectation here that's shown here. So we're just going to replace it with this expectation. So you can work through this yourself as well, but after replacing it with that, so we'll be replacing it with the expectation, right, over pi prime, right? We're taking the expectation of a pi prime of RT plus 2, right, plus gamma V pi ST plus 2, right? And this is again given S. So I guess there was no need for this. Let me just remove that here. Okay. So this is the stage that we're at with this proof, and now we are gonna break it down even further. This is equal to expectation over pi prime of RT plus 1 plus gamma, and we can actually take out RT plus 2 because it does not depend on pi prime, right, this expectation. So we can take out RT plus 2, and again we can take this out because this is pi, but it does not depend on pi prime. So this is plus gamma squared v pi st plus 2 given s, right? That's how it should be. And you can see we're essentially the same space that we were in before. We're in the same place. Here with rt plus 1 plus gamma v by st plus 1. Now with rt plus 1 plus gamma rt plus 2 plus gamma squared v by st plus 2. So you can see that this will actually keep on going, and you can prove it yourself by if you keep on applying this formula and this formula. Sorry, this proof is not what you call this. It might not be so clear to you right now, but just try to think about it yourself and work through it, right? And it should be fine eventually. So we have e pi prime here, and we have rt plus 1 plus gamma multiplied by rt plus 2 plus gamma squared rt plus 3 and so forth, right, given s. Now this is starting to look like something else. Expectation over pi prime of the cumulative rewards, right, that you'd get starting from this state s. Well, you already know what this is, and this is v pi prime of s, which means that, again, v pi of s, I'm running out of space here, but I hope you can see. Let me rewrite this again, somewhere maybe here. V pi of s should be less than or equal to v pi prime of s, if this holds, if we assume this. So this is the first thing that we assumed. So if we assume this, then this holds, essentially. And we know that this is actually applying to all states. So if this is the case, of course, if the value function says that the value function for v prime is greater, that means that pi prime itself, the policy, should be better. That's what the policy improvement theorem is basically saying in a nutshell, right? So with that, I'll move on to the next step. So you might be asking yourself at this point, like, why are we, okay, we have proven that according to the policy improvement theorem, if we make a change and it leads us to a better Q value, that means that the policy itself, the new policy, must be better, right? So the reason we're going through this now is we can now define what we call a greedy policy, right? So there are different kinds of policy. There's a greedy policy, there's an epsilon greedy policy, and so forth. We will go through some of them in the future videos. But right now, let's just focus on this one because it's the simplest to understand for now. So if we actually define our pi prime of s, right? If we define this to be equal to the argmax, right, over all actions, we're using argmax because we want the actual action, not the value, of q pi of s comma a, right? So under this policy, if someone gives us a policy, for instance, policy pi to begin with, and we evaluate it, then after evaluating it, we'll go like, okay, now let's take at some state or any state, or even maybe every state, we can actually apply this. But let's say some state, let's take the argmax over all actions, right, of q pi s comma a. And if this is actually greater than the value of that state under policy pi, that means that this new policy pi prime is better in that sense. So again, this will be just taking the argmax over all actions of, again, the expectation of rt plus 1, should write this better, rt plus 1 plus gamma v pi st plus 1 given s comma a, right? and this is again equal to the argmax over all actions of the summation over s prime comma r of p s prime comma r given s comma a times r plus gamma times v pi of s prime. So this is essentially where this leads us to. The same formulation we had here, we're just taking the argmax over all the actions. This is actually what the result of this policy improvement would be. This is how we improve our policy using a greedy scheme, actually. So this actually pretty much covers like what policy improvement is, and in the next video we're gonna go through the whole policy iteration algorithm. And after that we're gonna work through our first coding exercise using this algorithm to solve for the environment that we defined. Maybe we may change some things to the definition, but for now, thank you for your time.